Yeah, I think we are being recorded. Fine. So, okay. So let me tell you something about myself. So myself, I am Mayank Anupam. So I am a PhD student at Indian Institute of Technology, Kanpur. I am also a PMRF scholar. So those of you who might know, PMRF is a uh, it stands for Prime Minister's Research Fellowship. It is offered for PhD students, those who want to pursue PhD in government institutions. So for them, it is offered. So this is a scholarship that I'm also a part of. And as part of that program only, as part of that PMRF program only, we are here to hold sessions, hold these discussion sessions that I'm going to start from today. And yeah, so today onwards, we are going to start our discussion session here. The course is, as you all might have known, might have already started also. The course is Analog VLSI Design, taken by Professor Imran Mandal. So we will start. So I hope everyone has joined in. So today, since it is the very first discussion session, so it will be a light session only. I'll not be talking too much in this session. I'll try to keep it short since a lot of things have not been covered in the course. So I don't think there is much to discuss today, but still I'll try to address all your questions. Fine. So let me start by sharing my screen. All right. So is the screen visible to you? Maybe one of you can say something.
Yes,
Yeah,
sir.
fine, fine, fine. So again, let me again say what I wanted to say. So basically, my name is course name is Analog VLSI Design. Okay, and it mainly focuses. It is actually a slightly advanced version of any course that you will have on circuits. It is a slightly advanced version of that, wherein you will start learning how to make IC components, basically integrated circuit components, using basically in any basic level courses of circuits that you might have done, you would have seen things like operational amplifier or any amplifier kind of. So those things are kept in a black box or a box simply. So in this course, you will learn how to design that element. Okay, not in a lot of detail, but yes, you will be able to learn pretty much a lot in this course. All right, so that is the course. Now, the instructor for this course is Dr. Iman Mandal. He is a assistant professor in Department of Electrical Engineering at IIT Kanpur. Myself, my name is Mayank Anupam. I am also a PhD student in IIT Kanpur itself in electrical engineering. Fine. So some of you, I see there's a question in the comment section which is, can we get the recorded video of the meeting? Of course, you will get it. The whole point of creating this session and then recording, I am recording these sessions at my end. So I'll be posting all those videos on my YouTube channel, and you will get the link to those YouTube channels in, I think, next by next week. Okay, by next week onwards, you will start receiving the links of all the all the discussion sessions which we will have. The links will be posted on the same platform that you are using for doing the course, either so basically on the NPTEL platform. So nobody's there. If even if you miss something, even if something is missed because of network connection or anything, you can always go back and refer to the videos. There you will be able to understand things. All right. So what I will do today is I'll just try to summarize the various things that were covered in the in week one. Okay, and I'll also try to address some of the questions that were asked in the discussion forum that is there. So some people asked some questions in the discussion forum. So I'll try to answer those questions today. Okay, if you have any doubt, you can ask me. If you have any other doubt, you can ask me. Uh, all right. So let us start. Fine. So in week one, what all things did we see? So first of all, the instructor started with a brief introduction to the course and what can you expect by the end of this course. If you do the course, if you complete the course uh, with due diligence, then what is that you can expect from yourself? What will you learn at the end of this course? So that is something which he discussed. He said that, and I also reiterated it, that you will basically learn how to design an amplifier. Okay, that's the whole point of this course. So you'll learn how to design an amplifier. That's all. Now, after that, he started with other certain scenarios. He started discussing. As I already mentioned, the class will be recorded. Let me also type it in the comment section so that it is visible to everyone. Yes. Okay. Fine. So, all right. What was I saying? Yes. So, uh, so I start basically after that, the instructor started motivating for the course by taking different scenarios. If you want to create basically a voltage which is independent, which is like if you want to make a fixed voltage source which is dependent upon another voltage source. So, how do you go about doing that? Then he discussed what is the effect of loading, resistive loading on a network, and all those things. Uh, So let me start. Let me say something about it. So the whole idea of the whole motivation of this particular things is to say that let's say you want to, yeah. So let's say you want to get a voltage amplification. So if you have a voltage V in here, then there is due by some miracle here. Okay, you want to obtain a voltage which is K times V in. Correct? Now, yes. So how do you do this? Right? That was the whole point. And what all things should you expect from this voltage? So there are two questions. Okay. First of all, the first question should be how do you no. First question should be what are the requirements from basically this is the box, right? So this is an amplifier, right? What are the requirements from the amplifier? That is the first question. So anytime, this is a very basic. I mean, you all know this. I just want to say this out loud. So if a customer gives you something to design, okay, this is basically a design problem, isn't it? You want to design something which amplifies your input voltage and gives you an output which is the amplified version of your input voltage. So anytime that you have any customer asks you to design anything like this or anything, it may not even be an amplifier. It can be anything. The first question that you should ask the customer and yourself also is that what are the requirements from this particular block that you want me to design? Is it simply that you want amplification, or do you want something else also, right? Those things you should ask. So the immediate answer here would be that this amplification factor, it should definitely not be dependent upon anything that you connect after this, isn't it? So it might connect to another network here, correct? There might be another network here. So the whole point of designing a voltage amplifier is to make sure that whatever doesn't matter whatever you connect here in the at the output of the amplifier, the voltage here, the voltage at this point should be precisely controlled only because of the input voltage, correct? And it should be equal to some amplified version of the input voltage. That is the whole point of uh, making this amplifier, correct? So the first thing that you should definitely answer here is that we want a VCVS, or which is short for, this is short for voltage controlled voltage, sorry, source. So we want a VCBS, correct? Voltage controlled voltage source. I hope you all know this. A voltage controlled voltage source is nothing but the it is something of this kind. If I want to make a block diagram of this, so it looks something like this. You have a terminal, input terminal here. Sorry. Yeah, so those people who are asking me where the lectures will be uploaded, I again want to say I will be uploading the lectures or the discussion sessions on my YouTube channel, and you will be receiving the links to those YouTube channel from next week onwards. Okay, so I don't think you will be receiving the link to this week itself. You will probably be receiving them from next week onwards. All the lectures will be posted on my YouTube channel, and you will get the links to that. The links will be provided to you on the NPTEL website itself, the NPTEL course website itself. Yeah, so coming back to the point, so what is a VCBS? VCBS is nothing but you have a terminal here. Okay, so it is common and sorry. So let's say this is VI, so this will be some K times VI. Okay, so this is a VCBS. So whatever you connect at the, okay, so this is a VCBS. The voltage at port number 2, so let me also identify this. This is number 1 and this is number 2. Port number 1, port number 2. So the voltage at that you will see at port number 2 will only be dependent upon voltage at port number 1, and the dependency factor, it will be proportional to the voltage at port number 1. Proportionality factor will be K here. So this is a VCBS. So an ideal VCBS does not have, I mean, it has zero output resistance, isn't it? It has to behave like an like a true voltage source or ideal voltage source at the output side. So it cannot have. Okay, so let me see. Yeah, so it will not have any voltage. It will not have any output resistance here at the output. Ideal voltage control voltage source has zero output resistance. Okay, as you can also see here. So that is the whole point of, that is the question that we wanted to answer. So what are the requirements from the amplifier? We want a VCBS, isn't it? We want a VCBS, and a very good VCBS will have what? Zero output resistance, correct? So this is one thing. So can one of you quickly tell me what are the properties of an ideal VCBS? Can any one of you tell me what are the properties of an ideal VCBS? So this is very important. Yes, correct. So that is something which I already mentioned, that ideal VCBS has zero output resistance. That is true. What else? What else? It has infinite input resistance. Okay. Yes, infinite input impedance or resistance, whatever you want to say at this point, doesn't matter. So let's talk in terms of impedance only. I'm sure you all understand impedance. So good. So infinite input impedance, correct. What else? So voltage at port 2 is a linear function. Yes, correct. A function of input voltage. Correct. So all these things are properties of ideal VCBS. So the whole course started with the motivation to make a ideal VCBS. Okay, ideal voltage control voltage source. We want the output voltage to be some proportionality constant times the input voltage. That is what we want. Correct. That is the whole point. Okay. Now, what are some other dependent sources? Can you tell me? So I talked about VCBS. What are some other controlled sources? Can you tell me the names of those? So one is definitely VCBS. So basically, yeah. So as I already told, in this class we will be simply discussing some of the things which were taken in first lecture, and they might not even be. It can also be a refresher for whatever you have already learned in the previous courses. So yeah, so just try to answer these questions. Yeah, so it is a VCCS is another one which stands for voltage control
Uh,
current source. Yeah, that's VCCS. So what are the again, what is the symbol of VCCS? Let me draw it. So it's again the same thing, and you have it here. Then sorry. Yes. So again, this is your VCCS. So again, tell me what are the properties of this VCCS, ideal VCCS? Properties of ideal VCCS. You can unmute yourself and then say it's not a problem. Yes. So first one is R out should be. So I asked ideal VCCS. So in this case, R out should be infinity. Okay, there is no high or so. It's an ideal VCCS should be it should be infinity. Another one should be what? What about the input impedance again? What should be the input impedance? Since the input is,
Infinity.
yeah, again, right, correct. So input impedance again should be infinity because again it's a voltage. So at this point you want to sense a voltage, isn't it? So you want it to be infinite impedance. So again, infinite input impedance. That's good. What about the third thing? So in this case, you see, what about the relationship between uh, input and output? So output current to input voltage. What should be the relationship? How should it be? It should be linear, non-linear, polynomial. What kind of relationship should we expect? GM is so one comment is there. GM is not unitless. So yeah, GM is not unitless. I know. I just want to ask what kind of relationship. I mean, is it linear, non-linear? Should it be, yeah, correct. So it should be linear only. Yes. So the relation between output current and input voltage should be linear. Okay, good. Uh, Fine. What about now let's go to other. So what are the other sources? So to you said VCCS, VCVS. What are other these things? Yeah, so one of you has asked why have we considered R out here and not here? Yeah, so basically I have not shown in the figure here, but it should be considered here also. I mean, since it is ideal, so I didn't talk about it. So it should be this is R out. Okay, there's nothing special about VCCS. We R out can also come in the VCVS also. It's okay. In ideal, we do not have R out, so that is why we have R out equal to 0 in ideal case. Both and here R out is equal to infinity.
Can you repeat it that once again about that VCCS?
Come again, I didn't quite hear you. I could not understand what you said. I just want to understand. Could you please speak again?
Your voice is not audible.
Your voice is audible to me. My voice not audible to you? Is my audible to you? People, can you hear me?
Yes, sir.
Yeah, it's
Thank you,
audible.
thank you, thank you. Fine. So, Avinash, I think there is some problem at your end. You please try to. But I am audible to all the other people. Fine. So, what are the other sources here? So, we talked about VCCS, VCVS. So, what are the other sources? Yes, CCCS. Good. CCCS. So, what does it stand for? Current controlled.
VCCS.
Yeah, VCCS we have already discussed, right? Now it's time to discuss current controlled. Current source. Good. So again, the block level diagram of this one, how will it be? Hmm. What are the properties? As one of you have already pointed it out, CCCS has input impedance of zero input. Yes, correct. So in so basically again it has infinite R out, correct? And zero R in or zero input impedance. Good. So that, and what about the again the relationship? The relationship again is the relation is again linear, right? Linear relation between output current and input current. Good, good. The last one would be CCVS, as one of you have correctly pointed it out. CCVS, which stands for current controlled voltage source. What will that be? Oh, sorry. Hmm. What about this one? Again? Hmm. So here again the same thing, right? Zero R out and zero input impedance also. The relationship again is linear, right? Now, can you tell me something about the units of all the things here? Like K, what is the unit of K here? What will be the unit of K? Anyone? K will not be volts. K is unitless here, okay? K will be unitless. So K is unitless, okay? K is unitless. What about GM? What about GM? What are the units of GM? What will be the units of GM? You can unmute yourself and you can say, yes, so GM has units of Siemens, right? So GM is also called transconductance, okay? It's also called transconductance and unit is S, stands for Siemens, okay?
Why we use transconductance in current source?
Come again, I didn't understand your question.
Okay, I have written in the comment section.
Why we use GM in current source? So no, GM is just a nomenclature. It's a commonly understood nomenclature which stands for transconductance. Okay. Generally, if you want to like, you know that resistance. Okay. If you want to somewhere, if you want to denote a resistance, you generally go with the new this letter R, right? So similarly, if you want to mention a transconductance, you have to go for the letter GM. People understand that. It's commonly understood. I hope that was the question. Did that answer your question? Okay. Yeah, so 1 second. Yeah. So so basically why transconductance is commonly used. So yeah, see, basically here it's a voltage controlled voltage, sorry. It's a voltage controlled voltage source, isn't it? It's a voltage controlled voltage source. Sorry, it's a voltage controlled current source. So input is voltage, output is current. So what kind of a relationship do we have? It's not a simple proportional, right? It's a proportionality with a certain unit also, isn't it? Transconductance means the what is meant by a conductance? What is the difference between resistance and conductance? So what is the difference between resistance and conductance? The person that asked me this question about why transconductance is commonly used. So what is the difference between resistance and conductance? So digression here. Resistance, or rather, yeah, R is equal to 1 over G. Correct. So resistance is definitely the inverse of conductance. So you know that, and when you talk about when you say that something is a resistor, it means what? You apply a voltage and sorry, the when you say that you have a resistor here, it means what? On the application of voltage, or sorry, rather on application of a current here, okay, the voltage that you will be seeing will come at the same terminal, right? Where you apply the current, you will also see the voltage at the same terminal. That is a resistance. Now, what is a conductance? If you have a conductance G, what will happen? Here you will apply some voltage at the input, and you will see that the current is also consumed from the same place where you have applied the voltage. Okay, you get my point, isn't it? So that is a conductance. Why is this called a transconductance? Is because you apply a voltage at a certain point, but the current comes at a different point. Get my point? So at one terminal you applied a voltage here. At one terminal you applied a voltage. So this is where you applied a voltage. Okay, but the current is not coming here. The current comes somewhere else. The current comes from here, isn't it? From the other terminal. So it's a trans. So it's a transconductance. It's not a simple conductance. It's a transconductance. You apply voltage somewhere, but the current, the resultant of that voltage, the effect of that voltage is seen at a different port. So that is why it's transconductance. Good. So that that wraps up the discussion on this CCBS, VCCS, and all those things. Fine. So in this course, what you will see is that you will learn how to make. You will mainly learn how to make a voltage controlled voltage source. Okay. You will mainly learn how to make a voltage controlled voltage source, but you will observe that by the end of this course, uh, if you learn how to make a good voltage controlled voltage source, you can make all the others. So if you know how to make a voltage controlled voltage source, you will automatically know how to make all the other three. Okay, the other three controlled sources. If you know how to make any of the four, any one of the four control sources, you can derive the other from that only. Okay, so you will observe that this happens. Okay, now I hope you have understood almost everything that was taught in the class. So, but still, let's see some things that was not very clear to you all. I saw some questions with this, so that is why. Uh, yes. So let's talk about this particular thing. Let's talk about this one. Necessity of negative feedback for output control under variable load conditions. So did you all understand this properly? Could you appreciate the importance of negative feedback when you have loading output, sorry, when you have varying output load conditions? Yeah, Nikhil has asked me how to decide the unit of K and GM. Okay. See, what is the relationship between input and output here? So the output is a voltage, okay, the input is also a voltage, and these two voltages are related by a proportionality constant. So V out here, use a different pen color. So yeah, in this case, V out is equal to K times Vi, isn't it? So the input and the both the sides have the same dimension, right? So V out has voltage, Vi is also voltage. So naturally the dimension of K should be nothing, right? There should be no unit associated with K. It is a simple number, nothing else. Whereas in the second case, you have, see, in this case you have the output here is current. Okay, I out is equal to Gm times Vi. So here the left hand side dimensions are what? Ampere or current, right? And the right hand side dimension here, this guy has the dimensions of voltage. So what should be this Gm? It should be ampere over voltage, isn't it? So it should be ampere over voltage. That's how you decide the dimension or units of things. And ampere over voltage has the unit S, Simons. Similarly, a CCCS here, what will be the dimension? So I out will be equal to K times I in. Again, here what are the dimension of K? Again, unitless. But in the last case here, oh sorry, this is a voltage source, right, at the output. So V out is equal to some R times I in, right? So V out has the dimension of voltage, I in has the dimension of current. So R should have the dimension of voltage over current, or it should be ohms, right? Okay, all right. So Dhananjay has asked me when I will be taking the next class. So these classes, these discussion sessions will be held every week on Tuesdays, same timing, 6 to 8. Okay, and you will definitely be notified uh, one day prior to the session. Again, you will be reminded one day prior to the session that the sessions will be conducted. In case I am not able to take a session on a certain day on a certain week, you will be notified of that also. Don't worry about it. Yes. So Jiva, you have asked me how to explain transconductance once again. So yeah, so transconductance is nothing but uh, A conductance means you are okay. Let me. It will be better if I explain it here. What is a conductance? Conductance is nothing. Let's say conductance is this guy here, G. Okay, this denotes conductance. So what are the properties of conductance? If you apply a voltage source here across a conductance V, what is the current I? The current I will be G times V, isn't it? That is the whole point of a conductance. That is the whole meaning of conductance. And the other important thing to note here is that the the point of application of the voltage, okay, you have applied voltage across these two terminals, and what you will observe is that the current is also the result of that voltage being applied at across a conductance is the current here, right? And that current will also flow through the same terminals where you have applied the voltage. Okay. However, so this is conductance, but if you have a transconductance, so what happens here is that you will apply a voltage somewhere else. So this is Vi and this is Gm times Vi. This is the current I. So here what happens? Another Gm times V1. What happens here? Can you please tell me what happens here? Here you have applied voltage across this terminal, right? You have applied voltage across this terminal. However, the current that you are consuming is not flowing through this point. Sorry, different color would be better. A current is not flowing through this point. Please note, current is not flowing here. You have applied a voltage source at this point and the first terminal, but the current here is not flowing here. Current here is not flowing across the first terminal. It is flowing across the second terminal, isn't it? The point of application of the voltage and the result of that voltage application are different. That is why this is a transconductance. Okay, transconductance. Conductance means the application point, the voltage application point and the resultant current are both at the same point, same place. Here that is not the case in transconductance. Transconductance, voltage application and the resultant current are both at different places, different ports. Got it? Yeah, good. So I wanted to talk a little about necessity of having negative feedback for output control. First of all, I am sure you must have not, you must have heard about this term negative feedback. So have you heard about this term negative feedback before this class? Good. So some people have already heard about it. Yeah. So definitely in the basic circuit level courses, you must have seen this in op amps, negative feedback. So let us try to understand a little bit more about negative feedback. Excuse me for a while. Hmm. So let's see what is negative feedback. So what I will do today is I'll try to explain you, motivate you what is the point of negative feedback. What is the whole point of negative feedback? What do you intuitively understand with negative feedback? Okay, so that is what I will try to explain to you. So try to imagine the scenario that you are driving a car, okay, You're driving a car and you see you're driving a car on a road which has a lot of schools in between, okay, which has a lot of schools just beside the road. So there is a speed limit that is mentioned on the road. So speed limit is 40 kilometer per hour. Okay, let's say that the speed limit on the road is 40 kilometer per hour. You cannot go beyond this speed. However, you are getting late, okay, for your exam. You are getting late for your exam, okay, and this exam is not a simple exam, not an exam that you can miss. It's a, let's say, it's an exam, it's the exam which you have been preparing for like 4 years. So you do not want to miss this exam. But at the same time, your maximum speed can be 40 kilometer per hour. You cannot go beyond this speed. However, you also do not want to be late for your exam, so you do not want to reduce your speed below 40 kilometer per hour. So is the problem clear? You want to make sure that on this road you're always going at a constant speed of 40 kilometer per hour. You do not want to go less than 40. You do not want to go above 40. Otherwise, the traffic police will kill you. All right. So that's the whole problem that you have. Now, how do you do this? Generally, when you start driving a car on the road, what you will see, the moment you start, the moment you see that your speed is reducing, you want to put accelerator, right? So the thing is that, so now the whole problem is now of speed control, isn't it? You want to control your speed control to what? To achieve, okay, let's use a different color here under different space. Yeah, speed control to achieve a constant speed of 40 km/h. All right. So what will you do? First of all, if your speed reduces below 40 km/h, what will you do? If your speed reduces below 40 km/h, what will you do? You will simply do accelerate, right? Acceleration. You will simply accelerate. Look. You simply accelerate, yes? Good. Now, and similarly, if your speed overshoots, then what do? You decelerate, right? You decelerate, apply brake, yeah, anything. You do not want to apply brake, so if you apply brake, you will simply go down to zero. You want to just put your feet, just lift your feet from the accelerator. So that is how you will reduce your speed. So that is how you control your speed to achieve a constant speed of 40 kilometer per hour. Now, in all of this, tell me, what are you doing actually? What is the whole point of why am I talking about this particular case? Is this just to teach you how to drive properly, or was there a ultimate goal behind this? So there was an
uh,
ultimate goal, right? Yeah,
we are
go on.
actually getting feedback from output, and then we are sensing
Yes,
it to
correct.
accelerate or deaccelerate.
Yeah, yes, very good, exactly. That is the whole point. So the whole system here, which consists of the person who is driving, okay, the car, the accelerator, the speedometer. That is a very important part of the whole system. Okay, I have not talked about it. I didn't say anything about it, but the speedometer is also very important part of this particular system. Speedometer, right? That is how you see what is the speed that you are driving at. Anyway, so the speedometer, the driver, the car, the brakes, the accelerator, everything is a part of a system. And what kind of a system is this? is this? It's a negative feedback system, isn't it? What you're doing is you are taking feedback from you are taking feedback of the output variable that you're trying to control. What are you trying to control? You're trying to control the output speed of the car, right? You want to control the speed of the car, and for that, what you are doing? You are taking feedback, right? The output speed, you are taking a feedback of it, isn't it? You are trying to sense what is the output speed by using a speedometer. You are sensing it, and then using that information, using the information of the output speed, and what is the other information that you have? You know that you want to achieve a constant speed of 40 kilometer per hour. So if you want to just write it, so you have an output speed out, right? So you are observing this using a sensor, correct? So let's say this is your sensor speedometer. So using this you are sensing it, isn't it? And using this information, and there is another information also, right? You want to achieve a constant speed of 40 kmph, correct? Both of these informations you have, what do? You subtract these information. So basically, if the speed goes above the speed limit of 40 kmph, what do? You decelerate, right? You decelerate. So let's say this is accelerator, right? So if the speed out, if it goes let's say if it becomes 41 kmph, so what will the system say? It will immediately be sensed here, isn't it? The system speedometer will sense that it is 41 kmph. 41 minus so 40 minus 41 will become how much? It will become minus 1 kmph, right? So it means minus the output of this point, it becomes minus, means what? It means the accelerator has to become negative. You have to go give negative acceleration, which means you have to decelerate, isn't it? So, and you will decelerate till the point where your speed becomes again 40 kmph, correct? So this is how the system works. You take the feedback from the output speed, you sense it here, and then using the information that you already have and the feedback that you get, you control your system. You control your system to move in the direction so that the final goal is achieved. So that is what is negative feedback. I hope everyone is clear with that. Is there any doubt in this whole thing that I just explained? The idea of negative feedback, is that clear now? Yeah. So if negative feedback is understood, very good. Now one of you has asked, Muhammad Yasina B. So has asked, what about how would a positive feedback apply for this same example? Okay. So can one of you volunteer to explain what can be the situation where it becomes a positive feedback? How will the positive feedback look like here? When will we say that the system is not a negative feedback but a positive feedback? Okay, so if no one is volunteering, let me explain. Okay, let's say instead of again, first try to understand, imagine the scenario before doing anything on the notepad. So let's first try to imagine. So here I said that you want to achieve a constant speed of 40 kilometer per hour, but and how do you do that? You basically sense the speed. If it goes above 40 kilometer per hour, you decelerate it. If it goes below, then you accelerate it, right? But let's say you are mad, okay? You are just mad and you do not care anything about the world and say, I don't care. I will I'll do the exact opposite of what I am told to do. Let's say you want to do that. Then what will you say? If the speed goes above 40 kilometer per hour, I will again start accelerating. Okay, let's say you have that kind of a you have that you want to do that. If the speed goes above 40 kilometer per hour, I will simply accelerate. If the speed goes below 40 kilometer per hour, I will simply start decelerating. So let's say if you have that kind of a mentality, then you will never achieve your target speed, isn't it? You will never be able to achieve your 40 kilometer per hour speed. Is that understood? You can say that in that case, the system is positive feedback. Whatever feedback you are getting from the system, you are using it to generate an output which is again pushing the system in the same direction. Here what was happening? In the earlier case of negative feedback, what was happening? If the speed was increasing above 40, what were you doing? You were decelerating the speed, isn't it? You were decelerating the you were taking information from the output, and you were trying and you were doing something to the system which made it move in the opposite direction. Correct? So that is negative feedback. In the positive feedback, the thing that you will do to the system will try to push it in the same direction as it is going. Okay, so that is positive feedback. So in terms of this block diagram here, if the instead of a minus sign here, if it is plus, then it will become a positive feedback. So Muhammad Yasinabi, so did you understand this? If you did, please mention in the comment section. If not, also say what didn't you understand. Good, good. Thank you.
So basically, positive feedback when we are initialize the input, then the output will increase and increase and increase.
Increase
Is
or
this
decrease,
the,
it will whatever the disturbance is. Okay, the positive feedback will simply reinforce it, and it will keep pushing it in the same direction.
yeah,
Okay,
yeah, understood.
okay. The best one more example I would just try to put here
So
to
is this work like a oscillator when
yeah.
it's positive feedback?
So let me so that will come later. Okay, so let's not jump to that. But is this clear? The whole scenario that I was trying to explain. I
Yeah,
just
yeah,
want
yeah.
today
It's clear.
to explain what is meant by positive and negative feedback. That's all, nothing else. We are not going into the circuit level this thing implications of this. So there is another example which I will just say simple high school physics. So I am sure all of you must have seen this example. So let's say you have a ball here, okay, and you have a ball here, and this is a surface, okay, this is a surface here. Oh, yeah. So again, the same thing here. This is a surface, and let's say the surface is very smooth. Okay. Anyway, so what happens? So what happens if I push it in this direction slightly, and what happens in this case? And by the way, there is gravity acting. Okay, so do not assume that this is in space or anything like that. So there is gravity acting here, and this is the ground. This is the ground. Okay. So what will happen in both the scenarios? So in the first scenario, where the ball is pushed here, it will simply come back, isn't it? It will come back to the same point, right? Yeah, stable equilibrium, unstable equilibrium, correct. So in the first case, in case number one, it will again come back to the same point. It will always try to achieve the stable equilibrium point. That is the place where it should remain. Whereas in this case, the moment you give it a slight disturbance in any direction, it will simply try to go in the same direction. It will never come back. So this is a positive and negative feedback. Here there is, in this case, there is negative feedback, whereas in this case there is positive feedback. The disturbance, the moment it is disturbed, in the second case, the external forces try to push it in the same direction as the disturbance. It will never come back to the original place. Whereas in this case, the external forces will try to pull it back to the same place. Okay, So this is positive and negative feedback. Fine. So this is positive, sorry, negative feedback, and this is positive feedback. Good. So now that we have understood negative feedback, let me come to the point of necessity of negative feedback for output control under variable load conditions. Good. So I'll make it a slightly generalized thing. Okay, the instructor only explained about varying load conditions. So let us try to understand what happens in other scenarios. So what do you want to achieve? You have an input voltage, okay, and you have some RS, and you have a block here, and then you have some RL. Okay, what was this thing? How did Okay, so instead of this block, it was replaced with another thing, right? A simple, let's call it some R1. Okay, this was the scenario, isn't it? This was the scenario. Now, what was the problem here? Let's say you want to have a certain R out here. So this was the network. This was the sorry. Let's say you just put this R1 here, and you were getting some V out because of this R1. Let's say you wanted to have a voltage division of 0.5. So let's say you wanted to have a V out of 0.5 times V in. Okay. For now, imagine that you only want attenuating the voltage. You do not want to make a voltage amplifier, but you just want to make a voltage, have a voltage V out, which is some factor of V in. Okay, fine. So you want to have, let's say, 0.5 times V in. So what will be the value of R1? R1 will be equal to Rs, right? Now you will get a output voltage, correct? But the moment you start connecting this RL load resistance, what will happen? It will start taking some current, which and what will happen because of that? The V out will change, correct? V out will change. Is that understood? V out will change because of RL loading, isn't it? The RL thing, this here, will start taking up current, which will simply disturb the output voltage, isn't it? Fine, V out will reduce, definitely. V out will definitely reduce, yes. But you do not want V out to reduce, correct? So, in a way, what do you want? V out should not change even if RL changes, correct? If the RL is very large compared to RS, then there is no problem. But if RL is not that large, if RL is comparable to RS, then you have a problem. So in a way, what do you want? You want RL to be, sorry, you want this voltage V out to be a constant irrespective of RL. Yeah, so Preeti, you want me to explain it again? Okay, I'll explain it again. So what I was saying was, let's say you want a constant voltage V out at the output node here, which is 0.5, and let's say you do not have RL at the, which is, let's say, 0.5 times V in. Okay, so in that case, the value of R1 here, this resistor here, it will be simply Rs, right? If this voltage here, if this R1 here is simply equal to Rs, then V out will be 0.5 times V in, isn't it? There is no problem there. Now let's say you put a resistor here or load here, RL. Now what will happen? this RL will start taking some current IL, correct? This RL will start taking some current IL, and because of that, the voltage V out here will go down, isn't it? So basically, what is V out? V out is RL parallel RS divided by RS plus RL parallel R. Oh, sorry. Isn't it? This is a situation. Now, you know that RL parallel R1 will be approximately equal to R1 itself if RL is much greater than R1, correct? So if this load resistance here, if it is much larger compared to this guy, then you have nothing to worry about, because then your V out will remain whatever you wanted, which is 0.5 times V in. But in the other case where your RL is not that large, but it is comparable. Let's say RL is equal to R1, or let's say RL is less than R1. So what will happen in that scenario? You will have a problem, isn't it? You will see that your output voltage changes. So that is not a good thing. So what is your end result? What is your end expectation from the product? You want that the voltage at this point V out should be equal to 0.5 times V in and should not change no matter what you connect at the output. The load resistance can be anything that you that the customer desires, that can be connected outside, but the output voltage here should not change, should remain fixed at 0.5 times V in. So what do you do in that situation? So it's the same kind of question. Remember the same kind of question that we had here. You want to control your speed, no matter you want to achieve a constant speed of 40 km per hour, no matter what happens in the road. The road can be sloped upwards, it can be sloped downwards. You do not care about that. You always want to have a speed of 40 km per hour. Same is the condition here. Doesn't matter what is the load here, it can be very large, it can be very small. You always want a constant voltage here. So you understand the whole where am I going with this? So that is the whole point of making a, I mean, you definitely need a negative feedback here, isn't it? You need negative feedback. Correct. You need negative feedback in this case because the load can be anything. However, you want to make sure that the output voltage is not changing. You want some kind of negative feedback here so that the overall output remains constant. The output voltage remains constant. And the way to do this was by changing this, sorry, by changing the resistance here. So there was a different network, but the idea is similar. Okay, I just wanted to explain with this, so that is why I took a simpler case. So if you change RS, then in a way it can happen that your overall output remains constant, even if you change your load resistance. Got it? Fine. All right. So all of you understood this. I guess all of you have understood the idea of the necessity, the reason of putting negative feedback, the whole point of thinking that a negative feedback should be there to start with. In this particular example. I hope you understood this. Okay. Yeah. So that wraps up this guy. Now the last point. This I think a lot of people have doubt. Was this understood by all of you? What should be the property of a network for it to have power amplification? Good. If people understood, I just would like to again summarize it. because I saw some people asking doubts in the discussion forum. By the way, those people who had doubts in the discussion forum, if I didn't explain it today, you can just ask me now. Okay, you can ask me the question directly. I might forget, so that is why I'm saying just ask me the question directly. Hmm. So properties. Yeah, Kushalendra, Kaushal, you have raised your hands. What is the doubt?
Yeah, just I wanted to know whether since I joined late,
Uh-huh.
so I wanted to know whatever assignments is there for week one, whether that question has been discussed or not.
I have not discussed the questions. I will not be discussing the same questions that are there in the week one. I will
No, no,
discuss a sample of that question. I will discuss. Yes,
no, what I have in one question, no, I have some doubt. Question itself, I have some doubt.
you can ask
Since
me,
I'm
but
not,
let me finish
yeah,
this. Okay, I'll be starting with that in another 5 to 10 minutes. Okay,
okay,
I have
fine,
two questions
okay,
which are similar to the questions in the assignment. I have two questions planned to discuss today. Okay,
okay, fine, yeah.
yeah, thank you. All right. So this was the topic that was covered. Properties of a network for power amplification. So I will not be talking a lot about it because this was explained fairly simply and it was explained well in the lectures with a theoretical proof also, mathematical proof also. So I'll just say this so that it is explained well, understood well. Let me take an example, simple example. R1, let's call both of these R only, that simplifies a lot of problems. And this, let's call it another voltage V1, V2. Let's say V1 is given by uh, sine of omega 1t. Okay, let's say V2 is given by sine of omega 2t. Okay, Kushlendra, again, do you have another doubt? You have still raised your hands.
No, by mistake it got,
Yeah,
okay,
yeah, please.
yes, yeah. All right,
Fine.
okay, thank you.
Thank you. Thank you. So yeah, so let's say you have these two voltage sources and omega 1 is not equal to omega 2. Okay. Then now tell me what is the, oh, no need to have two resistor, you can have just one. What is the total power that is being consumed by our resistor here? What is the total power consumed by our resistor? How will you find the total power consumed by the resistor? What you will do? What do you do? How do you average? Ah, yeah. So by the way, it's average power that I'm talking about. Okay. I want to find average power. So what is that? What will that be? So this is actually very much motivated from the assignment that you have. So one is saying superposition theorem. So how will I apply superposition theorem? Nikhil Yadav. So you can maybe unmute yourself and say something about it. What do you mean when you say superposition theorem?
Like find individual sources, then add the power.
Okay, so let's do superposition theorem quickly. Superposition. And why did you say that you can apply superposition theorem here? Because the network is linear, right? The network is linear, so we can
Yes,
apply superposition theorem. Linear and
yes.
time invariant, right? So for superposition theorem, you only need linearity, no time invariance. Okay, you only want linearity for superposition theorem. Fine. So yeah. So let's say I just want to see what happens because of this V1. So R1. So what is the so yeah, superposition theorem you can apply. So what do I do next? By application of superposition theorem, what do I find here? What do I find here? Nikhil, what do I find here with superposition theorem?
Like we need to find out the current.
Current, okay, fine. Let's find out what is the current. So let's call it I1. So I1 is
I1 is V1 by R1.
V1 by R1. Good. So we know now this is the current. That is good. Fine. Now what about now what? Now what? So this is
Like
case number
power
one.
equal to I1 square by R.
Okay, power is equal to I1 square by R.
R1.
I1 square by R.
Yes.
Are you sure about it? It's actually I square R,
This will
right?
be I square into R.
I1 square into R.
Yes. So I1 square into R. Fine. So it's V1 square divided by R1. Correct?
Yes. Yes.
You want to find the average of this. So what will this be? Sine square of omega 1t divided by R1, average of that. So what is the average of sine square omega 1t?
Directly we can consider VRMS by root 2.
That you can do, but let's say I do not want to do that. So what will the square? What is the average of this? Tell me quickly. So if you want to find the average of this is very simple. You do not want to even if you do not remember VRMS and all those things, so that even that, then it is very simple, isn't it? It is 1 minus cos of 2 omega 1t divided by 2, isn't it? Into R. That the whole thing average, right? Yeah,
Yes.
Ayush Singh Rathod, you have a question? You have raised your hands. Ayush, do you have a question? You have raised your hand. Okay. If you don't have a question, just do not raise your hand. Yeah, so this is 1 over 2R, right? So what is the average of this? Simply 1 over 2R, correct? Because the average of cos of 2 omega 1t will be 0, isn't it? The average of any sinusoid is a 0, simple. So this is
Yes.
exactly the same as your RMS thing, right? 1 over 2 times divided by R. Fine. Now what is the second thing? Now second case will be that your R1 is this one. It's not R1, right? I made it R. Let's call it R, not R1. Yeah, V2. So what will power in this case be? Power here again will be 1 over 2R only, right? Isn't it? So total power is what?
1 by R.
Okay. Okay. This is what you did. 1 over R. Now tell me something. You said that superposition theorem we can apply and we can find out the individual powers and then add those individual powers that you said, right? So okay, let me okay, let's ask you. So even if you didn't know superposition theorem, you could have done this very easily, right? So you know that voltage across this is what? V1 minus V2, right? Isn't it?
Yes.
Yeah. So another way would be to simply take, let's call it third one. So other way would be what? The voltage across R is V1 minus V2, isn't it? So power dissipated in R is what? V1 minus V2 the whole square divided by R average, right? So I'm talking about average power. What will that be? Sine of omega 1 t minus sine of omega 2 t the whole square divided by R and take an average of that whole thing. So what will this be? Sine square omega 1 t plus sine square omega 2 t plus minus 2 sine of omega 1 t into omega 2 t. Correct? Am I right?
Yes, sir.
Yeah, good. Huh. And the whole thing, you want to take the average of the whole thing and then divide it by R. So the first average we already saw, right? 1 over 2R. Second average is 1 over 2R. So what is the average of this guy? What is the average of this guy? So this is where you will see that there is a problem in your earlier method. Okay, Nikhil. What you said was correct, but that there was a catch in that. In general, we cannot apply superposition. Okay, we cannot apply superposition directly to power addition. In power addition, superposition is applicable only for voltage and current additions. Okay, for power, you cannot say anything about that. You cannot apply superposition in general. The reason that your yeah, in this case actually it will be 0. And why it will be 0? So it will be 0 because sine of omega 1 and into omega 2 t, since omega 1 is not equal to omega 2 t, you know that this will simply factor out as omega 1 plus omega 2 t term and omega 1 minus omega 2 t term, both of which will be a certain factor, a certain integer number times t, which will simply become 0 after averaging out. But so that happened here because omega 1 of t and omega 2 were not same. Since omega 1 and omega 2 were not equal, that is why, am I audible?
Yes.
So since omega 1 and omega 2 in this case are not equal, that is why you saw that even after adding, simply taking individual powers and then adding them gave you the correct result. So here also you get what? 1 over r only. So this is the correct method. Okay, method 2 is the correct method. Method 1 can become wrong sometimes. Okay, it has a catch. You cannot simply take individual powers and add them and say that okay, power is simply the addition of that. That you cannot do. Okay, here you are able to add them because the cross term, this guy here, that became 0. That is why you were able to add them individually. So an extreme example of this I will tell you. The other example of this I will tell you where you will not be able to add them. I'll tell you an example of this. Wait a second. Yeah. Let's say in the same example here, let's say in the same example, that is you have a voltage source here, a resistor here, R, and another voltage source here. This is V1, this is V2. But now V1 is equal to sine of omega t, V2 is also equal to sine of omega t. Now, according to the method that you just said right now, Nikhil, here you according to your method, so let's call it again method 1, you will again get what? Average power is, according to your method, average power will become 1 over r, isn't it? Am I correct, Nikhil?
Yes. Yes.
Yes, right. But if you actually look at it, you will see that there will be no current flowing through this, right? Because both the voltages are exactly the same. So there can be no current flowing through the network, which means that the power dissipated in the network should be what? It should be zero, right? Which will be seen from the second method. You will see again, second method will give you what? V1 minus V2, another average power is equal to V1 minus V2 upon R, the whole square average, right? So what is V1 minus V2? It is simply 0, right? Divided by
Zero.
R. So it is 0, correct?
Yes, sir.
So basically this principle of superposition in power is not valid, okay? Superposition is valid only for voltage and currents in any linear network. It is not for power. In power, you can do this superposition thing when all the independent sources, that you have in the network are all operating at different frequencies, okay? So let me just make that clear here. You cannot apply superposition for power in general. However, if the network only consists of sources which are all independent, sorry, because of independent sources operating at different frequencies, then superposition will be valid for power. Got it? This is the whole point behind superposition. So this is a very important thing that I wanted to explain. Okay. So with this, we'll have a next. This, what was I trying to explain here? Yeah. So properties of a network of power amplification. So uh, now that you are clear on this, that if the network has different voltage sources, sorry, different sources operating at different frequencies, the frequencies cannot be same. So in that case, you cannot do power addition like that. Power superposition is not valid. So if that is the case, now if the network only consists of linear elements, if it is only linear network where the power superposition is in general not valid, and let's say you want to have a as an example, you want to have amplification in the network, so that now you have a V in here, which is AC source, and you want to achieve amplification here, K times V in, and you have some VDD here. If the network is linear, you cannot do that, isn't it? Because you know that because of this VDD, the effect of its power will simply come as DC power, right? As we just saw, because of because VDD is a DC power, DC thing, right? It's a constant voltage. It's, let's say, a constant DC voltage. Instead of VDD, let's call it VDC. It's a constant VDC voltage. Whereas V in maybe a kind of this kind of a signal, sine of omega t, right? where omega might not be equal to 0. So in general you will not be able to amplify it, isn't it? Okay, someone asked, okay, Nikhil asked me how sine omega or sine omega 2 term becomes 0. Okay, Nikhil, tell me something. Do you remember that thing which you learned in 11th class? So what is sine omega 1? 2 sine omega 1 2 into time into sine omega 2t. What is this? It's an identity. It's cos of, I think, I also don't remember very well. Cos of omega 1 minus omega 2, I think. No, it's not that. It's something else. So it's I don't remember the exact formula, but when you try to write the, if you go back and look at the identity, what is the sine omega 1 into sine omega 2? If you look at it, you'll be able to see that it's cos of something which will be, so it will be cos or sine of anything, what I don't know, cos of maybe omega 1 minus omega 2, and other term will be omega 1 plus omega 2t. Okay, this will be of this kind. So if there is a cos of omega 1 minus omega 2, and if omega 1 and omega 2 are not the same, in that case what will be the average of this across time? It will be 0. Okay, it will be 0. Similarly, if there is another sinusoidal term here, okay, and it will be addition of omega 1 plus omega 2t, it will also become 0 if you take the average of that. So you can go back and just look at it, okay, you will be able to understand this, figure it out, no problem. Yeah. Yeah, so that is what I again coming back to the point. If you have a sinusoidal voltage source here at the input and you want to amplify it, okay, but that amplification has to be provided by something, right? Because of power conservation of power, energy. You cannot get energy out of nowhere. Energy has to come from somewhere. So input energy is input. There is some energy, but you want to amplify the power of that. Input power has to be amplified. That power has to come from somewhere, isn't it? So that power, let's say we have another supply here, VDC. So we want the power to come from that supply, isn't it? But what will happen is, since your network is linear, and we already saw that in linear networks, what happens if the frequency of the independent sources are different, then the powers will not multiply, right? The powers will not multiply here. The powers will simply add, isn't it? So this will be DC power. Because of VDC, we will have a DC power. We will have a DC power, and on top of it, we will see that this sinusoid is coming like this. Correct? So if you want to look at the signal power itself, what is the signal power, or let's say the average power of this? The average power will actually be, average signal power will actually be what? It will be the same as the signal, isn't it? It will not change. It will still be the same. Not you will not get any amplification. Getting my point? This is what the instructor was trying to explain when he said that you want some non-linearity in the system for the system to start multiplying different frequencies together. Yeah, Jiva. So you want me to explain it once again. So what I was saying is, we already saw that if the network is linear, as we had here, if the network is linear, then the power, then the individual powers will add up, simply add up, when the independent sources are operating at different frequencies. Correct? That is what we saw here. That here in this case, the individual power simply added up. But there was no multiplication, there was no cross multiplication, correct? They simply added up to give the overall power dissipated, isn't it? Getting my point? Yeah. So, but if you want to see that in this resistor, what is the power dissipated in this particular example? The power dissipated because of this V1. the power dissipated because of V1 is simply 1 over R, right? And simply V2 is 1 over R, correct? This because the network is linear. There was no amplification of power dissipation, isn't it? You whatever power input was coming, so that much power it went here. The same way I am saying that if you have an input voltage here and the network is completely linear, there is no non-linearity, nothing here, then what will happen is any input voltage that you give here, because of that and because of this DC voltage, the output what you will see, because of this DC you will see that this DC will be let's say it will its power will be something, okay, there will be some DC power, and because of this sinusoidal thing you will have some AC thing, right? But if you only want to look at your signal power, right, the signal is not at DC, isn't it? This DC is not the signal, the DC is not the signal, the signal is what? The signal is this waveform, this moving waveform is the signal that you have. Now this signal will not have any power amplification as such, isn't it? Because the individual powers, they simply added up, they didn't multiply together, there was no frequency translation. The power that was provided by this DC voltage source did not appear, did not come at this frequency omega. It simply appeared at the DC itself. Whatever power you sent from your supply, it simply came at the same frequency, at the same DC voltage, DC level. The power of the supply was not contributing anything to the AC source, to the AC signal. That is what I am trying to explain here. That if the network is linear, then you will never have amplification in terms of power. Yeah, so this is what instructor was also trying to explain. So because of that, you want some kind of non-linearity in the system, so that the DC power that you will be getting from the supply, okay, that power can mix and then contribute to the overall power of the output signal, so that you have some kind of power amplification. Got it? Yeah. So basically, if you look at it closely, you just want what? You want some kind of frequency mixing, okay? Superposition cannot be applied to dependent sources. No, superposition was always applicable. Who said superposition is not applicable? Even if you have dependent sources, superposition is valid as long as the dependency is linear, okay? As long as the dependency of this control thing is linear, dependent sources, as long as the dependency is linear, you can apply superposition. Yeah, so I was saying that for you to have any kind of power amplification in the signal, you just want, if you notice here, you just want the DC or the supply power to manifest itself at the signal frequency, which means that you want some kind of frequency translation. If the network supports any kind of frequency translation, then you can expect, you can do something to achieve power amplification. Okay, so please note that. So only non-linearity is not, I mean, one way to achieve that is non-linearity, but there is also another way, which is time variance. You have generally heard about time invariance, right? LTI system, linear time invariant systems. But if the circuit is linear, but it is not time not time invariant, if the circuit is time variant, then also you can have power amplification. So something to simply think about. Anyway, So I think that wraps up the discussion here. Let's quickly go on to the questions that I wanted to discuss because I do not have much time. Okay, this is one question. This is another question. So I don't think I'll have much time to discuss the question. The person who had a doubt, Kaushalendra, Kaushal. Can you quickly tell me what doubt did you have? I'll just address that question only.
Yeah, just 1 minute. Yeah.
Yeah, let me bring up this thing. Yeah. So in this, what was the question?
This question number three, we can. This question number three, we can see. No,
What is VAB under question
I'm
two?
audible. Yeah, I'm audible to you.
Yeah, you are audible to me. Go on.
Yeah, what I'm telling, this question number three is there. No, question number three.
Yeah.
Yeah. So in that, whatever has been asked, no, what is VAB under QT condition in voltage with an accuracy of 2 decimal.
Yeah.
If V in equal to 1 volt, right?
Yes.
So it is nothing but if I see the waveform, it is being asked that what is the V Thevenin if V1 is the 1 volt. If I'm
Yes.
correctly understood the question,
Yes. Yes.
correct, huh?
Yes.
Yeah. Then next question I'll
No, no, no. 1 second.
then
No, that is not V Thevenin. No, no,
yeah,
no,
yeah.
no. It's actually. I mean, you will have to. It's not. How do I say?
Because I will
You see,
tell RL is
RL
not given.
effect. You see, RL. You cannot disconnect. You do not disconnect RL. Okay.
No, thing is that if you see question number two, no, RL is already we have considered it is much greater than the R Thevenin. So
Hmm.
effective effect of the RL is going to be
Okay. So in
neglected,
that
and then
condition,
only
yeah.
voltage.
In that condition, yes, 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 yes. It is actually V
No,
Thevenin. Yes.
that only I was asking. Then question number five is going to be like same only when it is very less. And
Yeah.
second, I got doubt here. No, this question numbering is how is done here because with question A, B, C, D is attached. No, that I am not able to understand. Is it in one
No,
figure
no.
A,
See,
B, C, D like it's associated?
it's okay. I mean, it's the same way, right? I mean, people have who I don't know how it works, but because I have not made the questions myself, but this ABCD probably was the number given by the people who framed the question, and probably 1 2 by was done automatically by the computer. So these things are done by the computer, right? So people have to give some questions, and then computer does its own thing. That is why probably 1A, 1 2B things
Okay.
came. Okay, so don't worry about that.
Mm-hmm. Okay.
Yeah.
Okay.
Anything else in any other question?
Then coming, one more question I had doubt.
Uh-huh.
Mm, Question number six. Can you explain little bit?
Question
Question
number
number six.
6. Find the Thevenin output voltage across VAB in voltage with an accuracy of
Mm-hmm.
2 decimal places when VI is equal to 2 volt. Treat question 5 result as
Okay.
ISC. Okay.
Okay. So that means whatever IRL we got, we have considered as ISC or
Yes, you have to consider ISC, yes. And then you have to
yeah,
find
that
out
is what. No?
what is the overall this thing you have.
Okay.
Is that clear?
Then, okay. This much only I had doubt.
Yeah, so
And
if you
this
do not have
about
any,
numbering as you already
it's fine. It's
numbering
number
system
is
already
don't
explained
worry
that.
too much about the
Yeah.
numbering system. Doesn't
No,
matter.
no. Yeah. Yeah.
Yeah. Yeah.
Okay.
So
Then
if
it
you
should
do
be okay.
yeah, if you do not have any other doubts, so I just wanted to say that I want to discuss a question similar to question number 8. Okay. I wanted to discuss a question
Okay.
I
similar to
wanted to
question
ask like there is one question like last two one how we need to solve.
the last, which is this part, right?
Yes, 16 and 17.
Okay, find the average power dissipated by delivered by BS1. So I just can you see something here? Can you notice something here? I just did a question like this, right? Two voltage sources, one resistor. What happened if they were if their frequencies were different? What happened in that scenario, right? I did a question like this.
Yes, here there are two different frequencies. So
You see, in general, okay, I'll just do this. Uh, I'll just explain here the mechanism, the idea. So I will not give the solution. So this question is slightly advanced version of that, right? You have another voltage source here. So there was voltage source, current source, another voltage source you have here. So it's a slightly advanced version. I would like you to try it. I will give you the idea how to do it. So I said that you cannot apply superposition for power in general, right? I said that, isn't it?
yes,
Yes. But if the network, if the sources, independent sources are all operating at different frequencies, then you can apply, oh, pardon my penmanship, so it's not good, isn't it? So here if you notice, there is one voltage is what? 1 volt. It's a DC voltage, right? It's DC voltage.
yes,
DC means frequency is what? Frequency is 0, correct?
yes,
The other voltage is omega naught T, means frequency is omega naught, correct? The
yes,
last one, the current source is also an independent source and its frequency is what? 3 omega naught, isn't it?
yes,
And omega naught is not equal to 0. Then in that case, since all the three independent sources have different frequencies of operation, can you apply superposition or not here in power?
we can apply, I guess.
Yes, you can apply. Don't guess. It is applicable here. You can actually apply superposition in power here because all the independent sources are operating at different frequencies. Okay, so the power dissipation, if you want to calculate in any of the elements here, okay, you can do that by simply taking the individual power due to due to the single independent element and simply adding them all together. Now, if you want to find out what is the power delivered by any of the sources, how will you do that? What is the power delivered by any source, voltage source? What is the exact formula of power? How is the power defined? It is V times I, isn't it? Average of that.
Yes,
So if you have an element here, it's actually applicable for anyone. So if you have an element here, and let's say it is plus like this V, and if you have current in this direction I, please note these directions. It matters a lot. It's very important. The direction here, the direction of current to the and the relative signs of voltage here is very important here. So in this case, the power dissipation in this element mind it, I am saying power dissipation. Okay, power dissipated in this element, average power. Oh no, not average. I'm saying simply saying power dissipated in this element is what? V times I. Okay, it's a positive number. Okay, let's say this I becomes in this direction. I goes in this direction. So what will happen here? This will become, sorry, do this. So if I changes its direction, so what will happen here? Minus V times I. Correct? Am I audible to you? Is that correct? The thing that I just did? It's called sign convention, passive sign convention. Okay, this is very important. Please note this. This way of defining power and all. This is called passive sign convention. This is passive sign convention. Okay. So according to passive sign convention, define the voltage in this way. The moment you define voltage plus, the moment you define a plus sign and a minus sign to the voltage, to the terminals of the element. Okay, the moment you define which terminal is positive and which terminal is negative, after that passive sign convention dictates that the current should be taken as positive when it enters from the positive side. Okay, the current has the moment once you assign a positive and a negative sign to the terminal, you then say that the current that we have here, the current will be assumed or understood as positive current only when it enters from the positive side and leaves the negative side. Okay, so that is why here in this case the power that came out here in this case was what? Plus V times plus I. Okay, which made it V into I plus, right? But when you have current going in the opposite direction, that is when the current leaves the plus terminal like this, in that case the voltage will still be positive. Sorry, the voltage will still be positive, however the current will be negative, which means this will become minus V times I. So according to passive sign convention, if you get a positive power, then it means that the power is dissipated in that element. Positive power means power is dissipated in that element, and negative power, it means that the power is being delivered by the element. Okay, I hope that clears things up. So now that you have that piece of knowledge in mind, here also if you want to find out what is the power delivered, okay, please note, we want to find out what is the power delivered by this voltage source V1. What will you do? You find out what is the current that is going out of this. Okay, then you find out what is the product V1 times I1. Okay, find out what is the current V1 times I1 and then average it. So that way you will get yeah, positive power means power dissipated, negative power means power delivered. But that particular thing, negative means delivered, positive means dissipated, holds only when you follow the passive sign convention. If you do not follow passive sign convention, then you cannot say that. If you have your arbitrary convention of if you have your own arbitrary convention of assigning signs, then you cannot do that. You cannot say that it is positive means dissipated, negative means delivered. Okay, you also always have to follow this passive sign convention, wherein once the first thing that you do for for passive sign convention is first you have to assign a positive terminal and a negative terminal to any element. Like in this case, let's say this resistor, I want to assign a positive node. So let's say this is positive, this is negative. Okay, so in that scenario, the current that will be taken as positive in this case for this particular resistor will be this kind of a current. Sorry, let's call this IR1. So if IR1 is flowing in the direction that I've just shown here, if IR1 is flowing through this direction, then we will say that IR1 is positive. If the IR1 turns out to be flowing in this direction, then we will have to say that IR1 is negative here. Okay. So this is passive sign convention. So how do you find out the power delivered by any source here? You find out what is the voltage across that terminal. Okay, find out what is the voltage across that terminal. Okay, and find out what is the current that is leaving that node, leaving the positive terminal. Simply product it and then average it. Similarly here also I1. So here also you assume that this is positive terminal and this is negative terminal, and then you find out what is the voltage across it and what is the current. Simply take the product and average it. You will be able to find the this thing. You will be able to find the average power delivered. I hope that clears.
So, sir, like here, do we have like a as voltage source will have both power delivered and power dissipated as?
Yeah. I'm not saying, I'm not denying that. So what I'm saying is this I1 is the net current, okay? Net current because of all the voltage sources and all the current sources. It's not like only because of this V1. Okay? When you take that, then you will be able to find out whether it is delivering or it is dissipating. Are you getting my point?
Sir, if it is dissipating, then by default delivering is zero.
No, that will become negative. Power delivered is if it is negative, which means it is dissipating. Are you able to understand what I'm saying? It's same as this one, same as this condition. I say that positive in according to passive sign convention, positive is power dissipated, negative is power delivered. But if you follow the convention that if the question is asked what is the power delivered by a network by an element, then you will answer it in terms of some positive number, right? If you are asked what is the power delivered by this voltage source, let's say it is around 1 watt. Let's say your power delivered is coming out to be 1 watt. Okay, so if let's say if the question was what is the power delivered by this voltage source, you will answer 1 watt. Okay, but after calculating another scenario where you calculated the power and it came out to be 1 watt dissipation in the voltage source, that can also happen. There is absolutely nothing stopping it. Okay, so that can also happen, that there can be voltage, that there can be power dissipation in the voltage source. So in that case, if you have the same question, that what is the power delivered by the voltage source, you will not say it 1 watt or 0, you will say it is minus 1 watt. Okay, because now the power is being dissipated by the voltage source, it is not being delivered by it. Are you getting what I am trying to say, Nikhil?
Yes, sir.
Yeah.
So like this similarly holds good for current source also, what you have explained here.
Yeah. Same thing holds. Yes.
Okay, like instead of voltage, you have current source that if it is like positive to negative terminal, it would be dissipated.
Yeah. It is, if the current is going from positive to negative terminal, the current is dissipated. Yeah. Power is being dissipated. Yes.
Okay, okay, sir. Thank you.
Yeah. Guys, I think that would be it for today. I wanted to discuss the questions, but I didn't get the time. No problem. I will discuss them next time. Okay. I will anyway be posting all these questions and everything on the. You will not get it immediately. I think it will be available to you from next week onwards. So I'll be posting it. All the things that I've discussed, I'll be posting it on my YouTube channel, and the notes I will be putting it on my drive. Okay, Google Drive. So you will be getting the access to these in probably from next week onwards. You can solve them in the meanwhile. Okay. All right. So yeah, we will discuss some problems from next time, definitely. We'll discuss the problems from next time. So today I just wanted to get a refresher from earlier times. So that is why I just wanted to do this. YouTube channel, don't worry about it. You will be told what is my YouTube channel. Everything will be available to you. Okay. Yeah, Nikhil, I will definitely be discussing the questions from next time. That is what the whole idea of this discussion session is. I wanted to discuss two problems which would have summarized the whole assignment. I didn't get time. It's okay, no problem. Anyway, so let's again meet next time. Or till that time, next time again. Next time we'll meet on Tuesday again. Next week. Okay, we'll meet again on Tuesday next week. Okay, thank you. Thank you very much. Hope to see you again next time.
Thank you, sir.
Thank you, sir.